So today on the Cyclo edition, we're privileged to be interviewing Dr. M. Christina White, who is the William H. and Jeanette G. Lykin Professor of Chemistry at the University of Illinois. Dr. White completed her PhD at Johns Hopkins with Gary Posner and then moved to Harvard for a postdoc with Eric Jacobson. Since starting her career at Illinois in 2002, Dr. White has been interested in developing highly selective oxidation reactions. She's a leader in the field of CH functionalization, having developed catalysts that affect selective oxidation by relying on subtle differences in the sterics and electronics of multiple CH bonds. Recently, the White Group published a paper in Nature where they disclosed a regio and chemoselective oxidative methylation strategy. So Dr. White, we're really excited to have you on the show and hear more about your recent methylation paper, as well as your research program as a whole.
Great, thanks so much for having me, Matt and Grace.
Yes, thank you for being here. So starting right in, what scientific questions are you most interested to answer in your group?
So as this slide sort of shows, this is my current group. We are a very synthesis-driven catalysis group. So we're really excited to develop practical reactions that will change the way scientists make molecules. In doing that, a lot of times we have to invent new catalysts and do things that in some cases people thought weren't possible before. So we also do things like study mechanism and try to uncover new reactivity and selectivity principles that perhaps had not really been, that had been previously overlooked.
Yeah, so you mentioned the types of problems that your group is interested in. What strategies have you used to solve those problems in the past years in your group?
Thanks, Matt. So I think, you know, as chemists, right, we have for centuries been very fascinated by small molecules that elicit biological functions. And so really, in a nutshell, we're very excited about developing reactions that enable scientists to use small molecules to discover function more rapidly. So, you know, what are ways that you can do this? So one way is to think about, you know, how does a molecule elicit function within the body? And the way that it typically does that is it sort of has a hydrocarbon core, a skeleton, and that hydrocarbon core is something that is filled with very strong carbon-carbon and carbon-hydrogen bonds. And in fact, so many of them that we don't even draw them in. And I think it's pretty obvious from this slide why we don't. And, you know, these, you know, carbon-carbon bonds and this hydrocarbon skeleton is really what displays the functional groups like oxygen to things in our body like proteins to elicit a physiological response. So we, you know, kind of asked ourselves, you know, what happens when you do atomistic changes like taking a carbon-hydrogen bond and introducing a new oxygen? Well, it turns out that this can change the properties dramatically of small molecules. It can change the way they taste, it can change the way they smell, and perhaps most interestingly, it can change their properties and take a molecule that was not a drug and convert it into a drug. So, you know, that got us to sort of ask this question: how is it that organic chemists introduce oxygen or introduce nitrogen, for that matter, into complex molecules? And typically what we do as organic chemists is we take pre-oxidized starting materials. Sometimes these come from nature, and then we repurpose this oxygen functionality. We use it to create carbon-carbon scaffolds while introducing new oxygen functionality and nitrogen functionality. So this is a really fantastic approach, especially if you have a specific molecule in mind that you would like to make. In many cases, you can access very complex molecules on much larger scales and much more rapidly than you could get them from nature, at least initially. However, if you are a chemist that is looking for function and would like to, for example, explore the Taxol framework and replace a hydrogen for an oxygen, let's say, this approach now has some real limitations, right? Because what it's going to require you to do is to resynthesize the molecule from scratch. And as you know, all of you perhaps either appreciate or will come to appreciate when you join a synthesis group, you know, doing one chemical step even is a very time and labor intensive process. And so you can imagine doing something like 37 chemical steps to make hydroxylated derivatives of something like Taxol is not really feasible as a way to explore for function. And so really that kind of limits the chemical space that organic chemists that are interested in looking for function can access in sort of a practical kind of way. So really what our lab aims to do is it aims to discover ways, practical reactions that can allow you to take, you know, what looks like a forest of CH bonds and take one hydrogen and do this atomistic change of converting it to oxygen, hopefully taking molecules that are not active and converting them into powerful new drugs. So that's what we are aiming to do.
Yeah, so you talked, and you've mentioned a lot about a late stage transformation to install an oxygen or a nitrogen. And many papers have been published recently that are doing similar transformations, but with enzymes.
Right.
How do you view the difference between like small molecule catalysis and the future of like enzymatic reactions?
Yeah, that's a great question, Grace. And I mean, that's really on point because that's, you know, really the way that nature does do it, right? So all of these, you know, systems that I'm showing you here, the key oxygen in nature is actually installed with those kinds of enzymes, with iron enzymes generally, and oftentimes P450s. And these enzymes are sort of ubiquitous. They exist in plants, in trees, in bacteria, and in fact, they exist in us. So right now, in your liver, you're probably metabolizing caffeine, maybe, if you had a cup of coffee. And so it's a very good question. You know, why wouldn't we, as synthetic chemists, simply use these very, very abundant iron enzymes to search for function? And so, you know, I guess the first question is, you know, how do these enzymes work? You know, in a very general sense, hydrocarbon oxidation, so CH oxidation, is a very high energy process. These are, in addition to being kind of ubiquitous bonds, which maybe you got an impression of when I sort of drew them all out on that structure before, they're also very inert bonds. So, for example, if you take a hydrocarbon in the air at room temperature, nothing happens. What you have to do, of course, is apply a lot of heat. And this is really combustion, right? So you get very non-selective oxidation that ultimately takes you to CO2. So what enzymes are really great at doing, and these catalysts are great at doing, is lowering the activation barrier of this CH oxidation process and achieving really, as you can see here, kind of remarkable levels of selectivity in doing this. So why wouldn't we use these enzymes? Well, you know, then the question becomes, how do these enzymes, you know, what is their strategy for the selectivity? And, you know, their strategy is through specificity. So, you know, let's take here an example of artemisinin. And let's say I want to oxidize it, and enzymes are known that do this at the C10 position. And the strategy of these cytochrome P450 enzymes is to create a binding pocket for artemisinin that will position this CH bond at the very high energy metal oxidant that does this oxidation to affect a CH hydroxylation process. So the issue becomes, what if, you know, as a, you know, pharmaceutical chemist, I would really like to oxidize something with a topologically and functionally different, you know, kind of motif or core, you know, like erythromycin. Well, you know, the enzyme that worked for artemisinin is likely not to work for erythromycin, right? Because it's very different topologically and functionally. So now I'm going to have to get a new enzyme specifically for this hydroxylation. So again, it kind of depends on what your purpose is. I mean, if you have one specific molecule in mind, this could be a great strategy. And in fact, there are many really remarkable examples of enzymes now being used in process development in pharmaceutical companies when there's a very specific target in mind. But if your goal, right, is really to broadly explore for function, you would like to do that with a lot of different types of molecules. And so, this approach may not be the best one. So, we thought a lot about that as a group when we started. And really, when we started our group, very prominent chemists that were working in this area, kind of felt that you had to use this approach. You had to either use sort of a molecular recognition approach, or you had to put a directing group on your molecule to direct where the oxidation was going to happen. Because, there was this very well-founded idea that there's very little difference in the reactivity between CH bonds, particularly CH bonds of the same bond type. And so I think, the meaning here was if you had sort of methylene CH bonds in a molecule, which you have a lot of those, that there's going to be very little difference in their reactivity. And that was very reasonable based on previous literature that really showed the only preparative examples of CH oxidation that achieve selectivity were ones with directing groups or, enzymatic molecular recognition type strategies. So we viewed it a little bit differently. We sort of took this analogy of, imagine you're in a plane and, you're looking down at a forest full of trees. And I ask you, okay, can you pick out one tree for me? You would say, no way, right? Because they all look the same from up here. But if you had the right tools, so for example, binoculars, you could see that, these trees are actually in different environments. So maybe some trees are next to a waterfall, other trees might be next to a lake, and then other trees might be next to a mountain. And so, what we really aimed to do was to find the right catalyst that could distinguish between CH bonds based on differences in their chemical environments, even if they were, kind of the same bond type, so very similar bond dissociation energies. And so, we were, kind of drawn to very classic physical organic examples and sort of the lessons that we learn as undergrads that, radical bromination is more selective than chlorination because you form a weaker bond. And so this goes through an endothermic process where you have a late product-like transition state where maybe the differences in the chemical environments of the CH bonds are more felt in that transition state. And we kind of felt that this was one of the big problems with hydroxylation chemistry, that most of the oxidants really were going through an oxygen-centered radical of some sort. And this was leading to very strong bonds being formed and very exothermic, unselective processes. However, very interestingly, take it back to your question about nature and about these cytochrome P450 enzymes, it's been calculated that the oxidant that they use, this iron oxo, actually goes through a very endothermic sort of late product-like type of transition state. And so we were very inspired by this. And so really what we kind of set out to do was to mimic this oxidant. And so certainly in sort of a very general sense, others had tried this before, and they tried it in, I would almost say kind of like in a literal sense. So what they tried to do was to rip out the porphyrin active site from a cytochrome P450 and say, well, we can just form the oxo in a flask, right? And, unfortunately, this, for some strange reason, didn't work. So you can see here, you get very poor reactivity. Really, no significant site selectivity based on environmental factors. And actually what was most interesting to us was how different this oxidant was from the cytochrome P450 oxidant. So for example, you form long-lived carbon-centered radicals that racemize stereocenters and open cyclopropane rings. You get a lot of auto-oxidation products, which are very reminiscent of Fenton chemistry, which is the chemistry of hydroxide radicals. So for whatever reason, right, the oxidant that, that this is forming is not like this iron oxo that is forming in cytochrome P450s, which is predicted to, should be very, very selective. And, we kind of hypothesized that maybe it was the fact that in the reaction flask, you can't mimic this cysteine ligation, and maybe that was part of the problem. So, but others, kind of had hypothesized that the problem was, the lack of this sort of molecular recognition element of the protein superstructure. So again, a lot of emphasis was placed on trying to recreate this molecular recognition element. So, we felt that this wasn't the place to be searching. So we looked in, I would say, a very different place. What we decided to do was to look at non-heme systems, which also make up a certain class of enzymes that do these hydroxylations in nature. And ultimately, this ended up being at least one of the solutions. So we discovered this catalyst, which is known as iron PDP. And this catalyst, is going through a very sort of biomimetic mechanism, we feel like. So we have done studies that have shown that the hydrogen peroxide and carboxylic acid come together at the metal center. And this carboxylic acid additive, acetic acid, is critical, we think, for promoting this oxo formation by donating a proton to the hydrogen peroxide and getting water to leave as a leaving group. And then this iron oxo carboxylate, which we believe to be the active oxidant, we think is in fact very analogous to a P450 oxo in that it's achieving a very late product-like transition state where now you can sense very minor differences in the electronic environments of CH bonds, the steric and stereoelectronic environments of CH bonds. So specifically, this iron oxo is very electrophilic. So it prefers to oxidize the most electron-rich site in a molecule, sort of irrespective of its bond dissociation energy, as I'm going to show you. Also, this catalyst now has an approach cone trajectory. So unlike the heme, it's not flat. The CH bond has to pass through this approach cone trajectory to hit the active oxidant. So you can also distinguish CH bonds now based on steric properties. We believe that this goes through a hydrogen atom abstraction to form this very short-lived carbon-centered radical. So that slightly sp2 hybridizes that carbon. And we believe that this now enables you to distinguish between sites based on stereoelectronic factors like releasing ring strain in the transition state. And then finally, if you remove acetic acid from your reaction mixture and you have a carboxylic acid on your molecule, this can actually act to direct the site of oxidation. So the other aspect of this is the recombination step, or the functionalization, right? So as I mentioned to you, I said this was a short-lived carbon-centered radical, just like you would form in an enzyme. And the reason we think this is because there's not even enough time to do a bond rotation before you get recombination or rebound of this iron hydroxyl. So all of these reactions happen with complete stereo retention in the hydroxylation step. So in addition to this being a really favorable property for maintaining stereochemistry in your molecules and not scrambling stereocenters, we believe that it also leads to the preparative yields that we're observing with this catalyst. So now you can take one equivalent of substrate and get out very preparatively useful yields. And we believe part of that, at least, is because this carbon-centered radical doesn't have time now to do other deleterious pathways, that it immediately recombines to form the product. So with this, now we have a very different view than we had before 2007. So unlike viewing this as a forest, iron PDP is really our tool that allows us to see CH bonds in a new light, and see them, for for the fact that they are in different electronic, steric, and stereoelectronic environments. And iron PDP actually weighs all of these factors equally. So when you have a site on the molecule that is very electron rich, relatively sterically unhindered, and activated through stereoelectronic factors such as alleviation of 1,3-diaxial strain, that site will be preferentially oxidized on the molecule, even in the presence of CH bonds that have a much weaker bond dissociation energy. We took this understanding then and developed a catalyst that now weighs one of these factors more heavily than the others. And so CF3 PDP now weighs sterics more heavily than electronics or stereoelectronics. And so now we can alter site selectivity for the first time, not having to change the molecule at all, but just simply changing the catalyst, and do so in preparatively useful yields both ways. In fact, this understanding led us to develop a quantitative predictive tool that allows you now to predict the site of oxidation, in complex molecules based on the properties of the CH bonds and how they interact with the properties of the catalyst to give the observed site selectivity that we see. So really this kind of led to a new area, which we're very, very proud of, and is something that, as you mentioned, Grace, is a very active area of research right now, this concept of late stage functionalization. So the ability now that we first demonstrated to take complex molecules either from nature or from the laboratory and directly make this atomistic change of CH to CO, and then explore that change for potentially new function. And you can see, you can do this, with a great deal of diversity that can be attained. We've also been very excited to see that others have taken this in different directions. So for example, streamlining synthesis, a concept that we put out in the early 2000s of, if you can introduce oxygen very early, very late in a synthesis instead of early, you can streamline the synthesis by not having to carry the oxygen through every single step and protect it, deprotect it, manipulate it. And you can see here many examples where this concept is being used with iron PDP to really affect some beautiful streamlined syntheses of complex natural products. So, ultimately what I would say to your answer, Grace, I mean, this was a very, very long explanation, but, what I would say, the thing that, a man-made catalyst can do that maybe nature's catalyst enzymes can't do is we can achieve selectivity with generality. And this can enable, people, chemists that are looking for function to rapidly explore function through this idea of this atomistic change of CH to CO. And you can see here in a wide range of different types of natural product settings and emerging pharmaceutical settings.
So shifting to your paper that you recently published on methylation, how did you get into that area of research, and why is late stage methylation important in areas like medicinal chemistry?
That's a great question, Matt. So, this atomistic change is not exclusive to oxygen. As Grace pointed out, it also is something that happens with nitrogen, and also, interestingly, with methyl groups. So it has been known for a very long time that if you take especially heterocycles and you replace a hydrogen adjacent to a nitrogen with a methyl group, that you can dramatically enhance the potency of many small molecule drugs. And so this effect, however, is it's not well understood, and it's not always predictable. And so, there's the desire to test it, but then there's also the recognition that there's going to be a lot of synthetic overhead that is associated with testing this. So, this is sort of the idealized path to introducing this methyl, but realistically, the way that people were doing this up until, now is that they were doing de novo syntheses, starting with simple starting materials that had methyls incorporated into them that would translate into the product. So some really tremendous work had been done in trying to do alkylations alpha to heteroatoms in heterocycles, and these typically went through a deprotonation alpha to the nitrogen, followed by a nucleophilic intermediate, and then trapped an electrophilic methyl or other alkyl groups. And I would say that this methodology has really been tremendous in terms of looking at a wide range of different alkyl groups that can be incorporated. However, the big limitation with the previous methods were the types of heterocycles that could be functionalized. And you can see this is pretty limited, and it's limited due to site selectivity issues and also functional group tolerance issues. And so what we aim to do is to really expand the scope of the heterocycles that could be methylated and the stage at which they could be methylated, meaning not at these very early stages, but rather at very, very late stages, either at the drug stage or very close to the drug stage.
Yeah, and I think we'll see, like, as you continue talking about your paper, or if our listeners have read this paper, that what you have done in this paper is very revolutionary to exactly what you were saying, where you can now insert the methyl group at a late stage versus that being often one of the very first steps of a synthesis, or having to go back and resynthesize the entire molecule to bring forward that methyl group. So how exactly did your group approach this strategy, and how were you able to accomplish this?
Yeah, no, that's great, Grace. And that was a really nice summary, by the way, of the paper. I think this is kind of a snapshot of what we were able to achieve. And I should point out, that this work would not be possible without two really phenomenal students in my group, PhD students, Kaibo Fang and Rondi Quevedo. This is a picture of when the paper got accepted. It's sort of a selfie, and when the paper first appeared online. So, these guys really get all the credit. They're the ones that really developed this strategy that I'm going to be describing to you. So you sort of asked what were kind of how this fits into our previous work and what were the previous advances that made this possible. So a little bit of background. I mean, one thing that I sort of point out, and maybe you guys, being as sharp as you are, noticed, but our previous work, we didn't have any aromatics in our molecules that we were oxidizing. And so another very talented student in the group before this work, Jinpeng Zhao, sort of figured out why that was. And the reason was that this iron PDP catalyst is very good actually at doing aromatic oxidations. And so you can see here, if you take this molecule and you try to do a methylene oxidation on it, really what you get is aromatic oxidation that's pretty unselective. So, this is sort of reflected in this chemoselectivity. And actually what Jinpeng found was that actually most of the oxidants out there that were reported to do methylene oxidations either had a similar problem or they were just very poorly reactive. And so, we started thinking about how to solve this problem in terms of, again, sort of relating our catalyst to sort of a biomimetic type of mechanism, and how does, nature, how do P450s oxidize aromatics? And so, P450s oxidize aromatics two primary ways. One is through an electron transfer pathway, and there have been some really nice studies that have shown that if you reduce the redox potential of this iron oxo and also make it more basic, that you can sort of shut down this pathway to some extent and promote CH oxidation. So we were aware of the fact that manganese oxos actually have a lower redox potential and also are much more basic. And so, this you can see just the simple swap of metals here of iron to manganese gave us a tremendous boost in chemoselectivity. So the other way that these P450 enzymes are able to do aromatic oxidation is to do an epoxidation. And so this pathway is actually a very sterically demanding pathway relative to CH oxidation. And so by now switching to this much more sterically demanding or encumbered ligand, CF3 PDP, you can see that our chemoselectivity becomes nearly perfect. But our reactivity is still quite, poor. So we went back again to our mechanism and considered the carboxylic acid and its role, right? So I told you that, we believed it was donating a proton and promoting oxo formation, and then it remains on the metal as a ligand during the CH abstraction step. And so we considered changing the electronics of the carboxylic acid. And you can see now by moving from acetic acid to chloroacetic acid, we now don't in any way deleteriously affect the chemoselectivity, but we significantly improve our overall reactivity, our yield. And so then we went back and checked, okay, do we need all of these components? And in fact, the answer is yes. It's a very sort of synergistic type system. So if you simply keep everything the same, but just change the ligand back to the simple PDP, you get a drop in the yield. If you keep everything the same and change the metal back to iron, you get a drop in yield and in the chemoselectivity. So with the system, we had demonstrated that we could now do, oxidations in the presence of these aromatic moieties in drugs and very strong bond oxidations, so these methylene oxidations to form ketones. So, this is kind of where we started, Grace. So we thought, we want to use this catalyst that now will allow us to do this kind of transformation on drugs that have aromatic molecules present in them. And we thought, if we could use this catalyst to hydroxylate such a compound, then this hydroxyl group, which is, you'll notice here, this is going to be a hemiaminal structure, potentially could be promoted with some type of an activating agent like a Lewis acid or fluorine to form an iminium. And then potentially this iminium could be reacted with, we hoped, a very mild nucleophilic now methylating reagent to give this product. Now, there were a lot of challenges actually in this pathway, and there were still a lot of challenges that remained in the oxidation. It was unclear what would happen if we had multiple sites open, including ones that potentially could be more activated, alpha to the heteroatom. There were chemoselectivity issues if we had, for example, neutral or electron-rich aromatics. So the previous system that did methylene oxidations could not tolerate neutral or electron-rich aromatics. It would still oxidize those. And then possibly the most challenging aspect of this was preventing the over-oxidation, so the oxidation of this alcohol to the ketone. So you recall I told you in our previous examples, we were going from methylenes to ketones, and we were doing that through a hydroxylated intermediate, which means this catalyst is a good catalyst for hydroxyl oxidation, right, to ketones. And so really this was one of the key challenges that we had to overcome in being able to affect this strategy. So then, we get to the second part, which is the methylation. And now, unlike the previous cases, right, we're using a nucleophilic methyl source, which is also going to be basic. And so now we're going to deal with things like potentially elimination as a side reaction. And also now, if we do have other electrophilic functionality, right, it can compete with our iminium ion for the site of alkylation. So, this is sort of what we faced. And so again, Kaibo and Rondi went through and overcame all of these challenges. And so, as you might imagine, iron PDP, as you would expect, gave predominantly aromatic oxidation, and manganese CF3 PDP, under the conditions that we originally reported it under, gave predominantly over-oxidation to this imide carbonyl. And so this is where one of the major breakthroughs came in, which was sort of the realization by Kaibo that we're dealing now with a very weak CH bond, an activated CH bond. So there may be the possibility of lowering the catalyst loading and lowering the amount of oxidant being used to try to, avoid this over-oxidation of the hydroxyl. And pretty remarkably, now at very, very low catalyst loadings, 0.5 mole %, he was able to effectively shut down this imide formation. And so when they looked back at this process, Kaibo and Rondi found that in fact, and again, I think pretty remarkably, this catalyst now is a much better catalyst at these loadings for doing activated CH bond oxidation than it is at doing hydroxyl group oxidation, which is, there aren't, as far as I know, many catalysts that would prefer to oxidize a CH bond versus a hydroxyl group. So that was, I think, really exciting. And here you can see, again, really remarkable substrate to catalyst ratio for this very challenging kind of transformation. So the next, I would say, big thing that needed to be developed is how do you activate this hemiaminal and prevent things like, elimination. And so one way that you can think about doing this, of course, is to use, make it into the hydroxyl into a better leaving group. And kind of a traditional way to do this might be methylation, but you can see we predominantly got enamine formation, which then tautomerized to this enone. So then we looked at, okay, can we just use a electrophilic and oxophilic Lewis acid? And BF3 etherate in combination with trimethyl aluminum worked for this methylation for this lactam. However, when you start going to more, sort of sensitive Lewis basic functionality like this carbamate on this oxazolidinone, what we found was a poor yield due to opening now of this oxazolidinone. And so now this was a significant challenge, the fact that we were getting now off-site alkylation at electrophilic functionality. And so, what we found was that instead of using BF3, if you fluorinated alpha to the nitrogen, trimethyl aluminum is a very fluorophilic type of organometallic reagent. And so now this could promote iminium formation, and now this coordination of the fluoride to the trimethyl aluminum could also promote this as an alkylating, a very mild alkylating reagent. And we found now using DAST or deoxyfluor that you could get very preparative yields now of things that had very sensitive Lewis basic functionality in them. And we also found other activation strategies, and this actually turned out to be a really critical part of this method. The fact that you can use different ways of forming the iminium, depending on the molecule that you're looking at. So having these choices really is what enabled having this kind of very broad scope that Grace mentioned. So here I'm showing you kind of the cores, and as I mentioned, you can use the DAST, which is shown in yellow, when you have a functionality that might be sensitive to a nucleophilic reagent. Otherwise, you can use BF3 etherate. But again, one of the advantages that I'll point out is there are cases like these piperidine substrates where it's not always predictable which activation method is the best, because it turns out that these are very prone to elimination to form enamines. So you can see, in one case here that I'm showing, BF3 is uniquely effective, but there are others that are very analogous where DAST was uniquely effective. So really this ability to, kind of look at both ends up really enabling this method tremendously. To point out some site selectivity, interesting aspects here. So we have many cases where we have substitution alpha to the nitrogen and much weaker bonds, and we always, oxidize and methylate at the site that is less sterically hindered. And you can see here an example where the substitution isn't directly alpha to the nitrogen, but beta, and even that blocks oxidation and methylation at that site. We can do this with drugs, drug precursors, derivatives, and natural products like peptides and terpenes. And the thing to point out here is really the remarkable chemoselectivity of this process now. So I told you before, at the previous conditions with the manganese CF3 PDP that we're doing methylene oxidations, we couldn't tolerate electron neutral or electron rich aromatics. Here, under these new conditions, you can see electron neutral aromatics and electron rich aromatics being tolerated for this process. So I do want to point out here that this was a collaboration that was done with Pfizer and chemists at Pfizer, two who are shown here. So this is Jeff and Martins over here. And really, they tremendously influenced this work. They really kind of showed us, what medicinal chemists are really looking for in terms of being able to do this method at late stages, and what types of drug scaffolds and motifs are most interesting to medicinal chemists. So I wanted to point that out here. Here, again, is another example of a complex pharmaceutical. Tedazolid is an antibiotic, and you can see here it getting methylated in a very preparatively useful yield. I will point out that we looked at the precursor of tedazolid, maybe anticipating that this very nitrogen-rich heterocycle portion would not be tolerated. And we were very, very excited to find that actually we got comparable yields with the precursor as we did with the actual drug itself. And you can see that this reaction scales very nicely, just as the previous ones do. So we're able to do this on gram scales, no problems. We were able to do magic methyl substrates. So again, here I'm showing you the ability to introduce methyl from this very advanced RORC precursor. And again, typically medicinal chemists would do this starting with a very simple commercial building block, but having to remake the molecule from scratch. So, I think one of the next things people are sort of interested in is what are the sort of new directions for methylation. And I think certainly one of the new directions is being able to introduce methyls, with intermediates other than just very activated iminium or oxoniums that we've shown with this method. And so, we do have some hints in this paper of ways that you can do that. So for example, in this magic methyl substrate, you'll note, that we are now going through an imine, which is a less activated electrophile, obviously, than an iminium. So, with this imine, we had to use a stronger nucleophile, actually a Grignard at cryogenic temperatures, but we were able to methylate this very advanced, this drug directly using this method. And then ultimately, one of the things that we're very excited about is introducing methyls now on carbocyclic cores, on unactivated aliphatic CH bonds. And so here is again another potential hint of how you could do this that we sort of published in this work. So as I mentioned before, this catalyst is capable of doing oxidations on strong aliphatic CH bonds. And so in this case, because of the substrate itself, we stop at the hydroxylation and we get a diastereoselective hydroxylation here. And so actually Kaibo noticed that from old literature, that the combination of a mesylated hydroxyl with trimethyl aluminum could affect a methylation, presumably going through a carbocation intermediate. And what we found is that same sort of combination could affect methylation here. And you can see again, the ability to form one diastereomer, potentially because of substrate control, and the direction of methyl group attack. So yeah, so that's sort of the future directions, I think, some of the things that we're most excited about pursuing next with this work.
Awesome. Yeah, I really appreciate that detailed explanation. I'm definitely not an expert in this field. And when I first read your methylation paper and you used manganese rather than iron, which is kind of what I'm familiar with, I didn't exactly know why the change was made. So yeah, thanks for that explanation.
So over the course of your presentation so far, you've discussed making carbon-oxygen bonds, carbon-nitrogen bonds, now carbon-carbon bonds for the methylation paper. Where do you hope that the field of CH oxidation reactions are going to go over the next 20, 50 years?
Yeah, that's a really great question, Grace. So, I think one of the things that we've been most excited about, or one of the things that we've been very excited about, is just to kind of observe, what a paradigm shift in effect, our work has had on the community in terms of especially how the community views the reactivity of inert aliphatic CH bonds. So, if there was one thing that I guess we would like to be remembered for, it's for changing the community's perspective in this regard. And so now, because of this work that I described for you, I think a lot of people now, except even people that really didn't believe it at the beginning, sort of are now, kind of writing review articles and talking about how it's possible to distinguish CH bonds based on their, environments. And so, we've been very excited to see, other prominent researchers using kind of these rules, to affect, as you mentioned, kind of site-selective CH acidations. We've also used it in other ways for alkylations as well as aminations, and we've shown similar types of rules in those processes as well. So for example, in this benzylic amination, we've shown the ability to select between benzylic sites based on properties like electronics and also sterics. And so, I think this is one of the great future directions, is trying to develop catalysts that will continue to change the site of CH oxidation, amination, alkylation, by changing the catalyst and not having to change the molecule, and still being able to do this with a lot of generality and predictability. So that's one of the things that we're very excited about. I do think that also going through other mechanisms will enable other types of unique reactivity and selectivity patterns to emerge. So in our group, we've had a long-standing program of doing allylic functionalizations, going through carbon metal intermediates, specifically carbon palladium intermediates, these palladium pi owls. And these systems have really highlighted for us some sort of future directions in our other oxo and nitrine and carbene type work, which is, doing these types of bond formations with asymmetric induction and being able to control it based on the catalyst properties. Also being able to use CH functionalization, not just as a way to introduce functionality, but as a way to do cross-coupling reactions. So, in several of these cases now, we're able to take very complex fragments and bring them together through CH functionalization. So I think all of those are kind of very exciting new directions in this area.
Yeah, I think that's really powerful, and just seeing the progression of your career and how that's influenced so many people, and the way that we think about the different CH bonds is so inspiring to everyone, especially young chemists like us.
Thanks so much, Grace.
So I guess with that, these were kind of our questions that we had prepared relative to science, and we just kind of wanted to end on like a positive, fun note.
Yeah, that sounds great.
So first, we just wanted to hear, what's your favorite place to eat in Urbana-Champaign?
Yeah, that's great. Yeah, hopefully you guys will cut a chance to come here if you haven't been here already. I know many of you were people that we were trying to recruit to come here. Yeah, so this is my current group, and first of all, I just want to say that you guys maybe know this, but for the PIs, our ability to work with students like you, and students like the ones in my group that are just so driven and excited to kind of change, chemistry, and change the way we make molecules, and change the way that we think about chemical reactivity. I mean, that's the best part for sure of this job. So this is my favorite place to eat. This is this place called Pizza Antica. And so it's, very, very low key, as you can see from this picture. And this was kind of a group celebration where we went there to kind of celebrate. I had just gotten a chair. So we were all there to kind of celebrate that. And it was a lot of fun. So it's really good. If you ever get a chance, they're homemade pizzas, and it's a really nice laid back kind of environment.
Congratulations on the chair first. That's pretty amazing.
Thank you. Yeah. And these are, so this is my group, and then these are my sons. So this is Leonidas, and this is Todoraki. And they were sort of the life of the party, as you can sort of see from this picture.
That's fantastic. So when you're not doing science, do you have a favorite place to travel or a favorite place to vacation?
I do. So, yeah, so it would definitely be anywhere in Greece, but, I'm actually from Greece, but I especially love the Peloponnesos. So if you guys have not been to Greece, it's not a place that many tourists visit, which I think is unfortunate, but it's one of the most beautiful places. So it's southern Greece, and there are beautiful beaches. So this is Zaharo, and it's a beautiful beach. There are amazing sort of historically relevant places to see. So this is Mykonos, which is where the Mycenaean civilization sort of started and was rooted. This is Nafplio, which is a city that is kind of you just walk around, and there are just pieces of art everywhere that you can sort of, as you can see here, interact with. So yeah, so I think if you guys ever get a chance to visit, especially this part of Greece, it's really extraordinary.
That looks awesome.
Oh.
Do you have, on the other side of that, a favorite university to visit?
Yeah, so I would say someplace very far from Greece, but probably I would say Harvard. So, as you guys mentioned, I did my postdoc at Harvard. I didn't overlap with Tesheg, but it was an incredible place to do science in the Jacobson group. This is Eric's 60th birthday party / reunion. And, all of these amazing scientists that are part of this family and that I got to interact with while I was there really shaped who I am today as a scientist. And obviously, Eric, very much shaped who I am today as a scientist. So just for very, I guess, for those reasons, going back is like going home. So I always really love going back there.
So last question. If you go to your website, you see these things called group posters, right? Which are for recruitment.
Yes.
And they're pretty awesome. Yeah, you have one there.
This is the most famous one. Yeah.
So how do you come up with these? What's the inspiration?
Yeah. So, this actually, again, goes back to Harvard. So when I was there, many groups were sort of into this, like kind of on and off. So it would be kind of a fun way that we would advertise our open houses. So, I'm not sure if that's something that you guys do at Wisconsin, but here and also at Harvard, we would every fall, each group would have an open house, and the open house would be an opportunity to interact with the incoming students and for us to kind of present, the work that we've done, the work that we hope to do, and just kind of introduce ourselves as a group. And so it was just a fun thing to try to come up with a really interesting way to express the science that we did in sort of maybe a non-science way, right? And so the inspiration for this poster obviously is, one way to think about oxidation is you're combusting things, right? So if you burn something, you're oxidizing it. And so that was sort of the inspiration for this poster, which I can't take credit for. Actually, this guy named Nick Vermeulen, who is now a chemist at Corteva, is the one that actually came up with this idea. And he actually, these lab coats, we actually did paint them black. And so a lot went into this particular poster, which ended up being one of my favorites. So
that's fantastic. Yeah, we definitely do that at Wisconsin too. I think
you do.
Last year, someone photoshopped Teshik onto a Drake meme. So.
That's great. That's really great. Well, you guys should post them because we would love to see. We would love to see yours. So
we definitely should. Yeah. Well, with that, I just want to thank you for coming on and spending time to talk about your research and your non-research as well.
Yeah.
And just thank you so much for your time.
Thank you guys so much. These were great questions and I really enjoyed it. And, thanks for doing this for the community. I think it's a wonderful thing to have. And I know a lot of my students watch it and I'm sure that a lot of students are really benefiting from this. So